Good afternoon, guys. I'm Steve Musa. I'm one of the project team for CCUK. It's a predominantly technical presentation today, so it's going to be run in the main by my colleague Jayesh, who's just appeared. Hi, Jay. Good morning.
Good morning, good afternoon, everyone.
Yeah, it's morning over here in the UK. Just give you a bit of background. I'm in the northwest of England, Liverpool. Jayesh is up in the northeast of England, a place called Hull. It's a bit further up north. So thanks very much for taking time to join us this morning or this afternoon. The presentation that we're going to be focusing on today, the use of carbon fibre in the construction industry, obviously in the UK, and the focus is going to be on buildings. So what I want to do very quickly is just to run through the presentation objectives. We'll look at the business sectors that we work in the UK, the business divisions that make up CCUK, the design principles. Obviously, this is key to the presentation, what you guys are here to listen to. This is running the main, obviously, by Jayesh and that. I always like to point out to our clients in the UK, the design is ours. We take on the risk. We take on the liability. This presentation is about ideas. We don't know what projects you've currently working on or you've worked on in the past or maybe coming down the line. So hopefully today it will give you an idea of how to design a solution, how to use carbon fiber on your project. We'll look at what we can strengthen. We'll look at what we can strengthen, the various aspects. We've got some really good project examples, which includes time-lapse video, and then at the end, after about 40 minutes, hopefully, Q&A session. So let's kick off on the presentation side then. I'll look at the business sectors that we operate in the UK. And by far the largest is building and construction. We class it as adaptive reuse. So where you've got an existing structure that you're going to turn into potentially add additional stories or floors onto it. You maybe turn it into a hotel or apartments. Adaptive reuse type projects are huge in the UK. Especially in London, probably 80% of our current business is based in the city of London. The engineers and the construction teams, the main contractors, they get it, they understand it. London is now looking at more or less phasing out the demolition of buildings, and they're looking to reuse wherever they can. Transport and infrastructure in the UK is bridges. So if there's any bridges which are being damaged or could be damaged potentially from impact, we do work there. This is where we came from. We used to be an American-owned company. We're now privately owned in the UK, but obviously in the States, anywhere where there's potential for seismic activity, and that was how it was developed. Jay shall go into that in a bit more depth later on. Waterfront structures in the UK, if any of our clients have assets that can be or are being damaged by water, this is something that we look at also. The power and energy side of our business is very small, but we always like to mention this because we do work in the nuclear industry. And just to get to the table, just to do work or to bid work within the nuclear industry is very important. It's critical to be able to do that on the quality side. Pipelines and water storage, again, in the UK, that's the water companies. In London, it's Thames Water. Up here in the northwest, it's United Utilities. So we're able to do work in the water industry, but only in the UK, we would work on water sewage or dirty water, as we call it. We don't do clean water in the UK. So today, we just said we're going to focus on the building and construction side of our business. I'll just give you a bit more information about CCUK as a company. Obviously here to talk about the carbon fibre and the carbon fibre strengthening side. But as you'll see during the presentation, a critical part before you can apply carbon fibre on any asset, the concrete has to be brought back to life. It has to be in perfect condition before you can apply carbon fibre to it. So we have a concrete division which has grown up alongside with the main contractors. We're obviously not going to be speaking about that part of the business today. The focus will be on carbon fibre and carbon fibre strengthening. The final slide I'll mention is, again, in the UK, we look at the environmental side, the environmental impact, especially in the planning and early design stages. And this is just a few points that designers and main contractors in the UK are focusing on. Why demolish if you don't have to? You have to look at reuse or extend or refurbish the asset. When you're looking at production cost as opposed to 10, 15 years ago, production costs, it's a lot cheaper to produce carbon fiber than if you're looking at concrete or steel. When you're on site, when you're on a construction site in the UK, we don't need large craneage or transportation to bring our equipment and materials into site. So therefore, using carbon fiber gives you a smaller footprint, which again environmentally is critical. And then finally, well, when carbon fiber comes to the end of its design life, what are we going to do with it? How are we going to recycle it? There's millions being spent currently year on year in the US and Europe. We're looking at ways of how we can recycle. Currently, at the moment, it's a situation where it's taken off and removed and crushed, but other methods are being looked at. So that's the introduction. That's just a brief introduction. I'll come back on later on the presentation. As I said, this is predominantly a technical presentation, so I'm going to hand you over to Jayesh now. Thanks, Jay.
Thank you, Steve. Good afternoon, everyone. I'm Jayesh Nandwana, Technical Director from CCUK Fibrwrap. I'm responsible for the design of carbon fiber strengthening system for the various projects we do in the UK and Europe. So I'll deliver this presentation. The whole purpose of doing this presentation is to explain you the concept behind strengthening with carbon fiber strengthening system, or FRP in general. So that's the reason why I'm delivering this presentation. So before we go into too much detail of the actual presentation, project case studies and all those things, I just want to start from basics because I'm not too sure how many of you have worked with FRP design and FRP strengthening in past. So it's better to start from the basics so everybody understand what it is. So carbon fiber reinforced polymers, commonly known as CFRP or FRP in general, are very high strength and lightweight systems. But the most important thing to note here is that this is a composite material. The basic composition is a fabric mixed with epoxy matrix, and then you apply it onto the structure from the outside of a structure. That's why it is called externally bonded reinforcement, or EBR for short. You can use carbon fiber strengthening or FRP strengthening on concrete, steel, wrought iron, cast iron, even on timber structures. So pretty much all type of structural construction materials can be strengthened with FRP. Now, just to give you a feel in terms of number, carbon fiber is at least 3 to 4 times stronger than steel and at least 7 to 8 times lighter than steel. So you could see this strength to weight ratio, and why people prefer to use FRP over traditional methods these days is purely because the time in doing that strengthening is much, much less as compared to the traditional method. The other misconception people generally have is that FRP is a new material in construction and it's a new technology and all those things. In reality, it's not true. This was first used in 1944 in aerospace engineering. Then they started making all the aeroplanes, fiber boats, motor cars using FRP. And in 1988, this was first used in construction. And that was basically a research project in University of California, where they wanted to find a solution to save their bridges from collapsing due to earthquake. So that's how basically FRP came into construction industry, and they did a research in University of California. They found this solution, and then since they started using this for strengthening structures worldwide. The other advantage of using FRP is that it is very low profile material. The typical thickness of one layer of carbon fiber is around 1 millimeter. So imagine if you're able to strengthen a beam, column, or a slab with one layer of carbon fiber, it means you're increasing its dimension by just a millimeter. So which is negligible in overall scheme or grand scheme, and that's why architects prefer to use this as well. And finally, the question which everybody asks, that how much it is going to cost if they are going to use FRP instead of traditional steel or concrete. Then in that case, we see that if you see the whole cost in terms of material, labor, disruption to the structure, and most importantly, time in doing that strengthening, then FRP is the most economical solution available in the industry at the moment, because it saves you a lot of time and ultimately the money. Right, we'll go in a bit more details of in terms of design guidelines, approvals, and acceptance. So in terms of the approvals, how do you know that which carbon fiber or FRP material you should use in construction or propose to be used in a construction project? So at least here in the UK, the least approval any of these systems need to have is the CE marking. That's the least approval those systems need to have. In addition to that, there is an international approval which pretty much, all the major carbon fiber suppliers have. So that is ICC approval, which is International Code of Council, the governing body for design codes around the world. So they provide this ESR listing. So some of the systems have this. UL approval is basically for fire protection systems of FRP. So if somebody comes to you with a fire protection system over the FRP, you need to check for this UL rating, that what sort of UL rating that system has got, because that's the authority which provides the approval for that. Now, in terms of design, if we're designing it in the UK, then the document to follow is this Concrete Society document TR55. That's the design guideline to design FRP in the UK. There is ACI 440, American Concrete Institute document, majorly followed in America and worldwide. So I presume if you do project in South Africa, I think you'll probably end up designing it based on ACI. And FIB Bulletin 14 is followed in the rest of the Europe. So these are the three main design guidelines which are used worldwide to design FRP. Now, if you note, I'm saying they're design guidelines. They are not design codes. So there are different countries who has their own design guidelines. For example, Canada have their own guideline, Switzerland have their own guidelines and all. So at the end of the day, there is not a set code to design FRP. So for example, a Euro code or a BS code or something like that. And for that reason, you don't see too many people or engineers designing FRP as a common material, because you don't have a set parameter, so based on which it can be designed anywhere in the world. So to change that, a team which finished the TR55 latest edition was working to put an annexure in Eurocode 2. And there has been one annexure already included. I think it's called annexure J in Eurocode 2, which is the FRP design for strengthening structures using pre-cured materials. Then also they are putting another annexure in there for the design of FRP fabric systems. So soon we are going to have a Eurocode 2 to design FRP, and after that you'll see it is becoming a very common material to be used all over the world. Now, just to show you the material types, generally carbon fiber comes in two forms, or FRP generally comes in two forms, especially for strengthening structures. So one is like a fabric system, which looks something like this. So it's a dry fiber of carbon fiber, which comes on site on a roll along with the epoxy. So you can cut it in any size and shape you want, saturate it with the epoxy, and then you apply it onto the structure in its wet condition. So the application is called wet layup method. Then there is these pre-cured carbon fiber plates. You guys may have come across carbon plate bonding in past. You may have read about it or may have used it as well. So in plate bonding, what you just use a pre-cured carbon fiber plate. So similar to like a steel plate, but made out of carbon fiber. So all you do is you apply epoxy on top of it and then bond it onto the substrate. So that could be a slab strengthening, beam strengthening, or whatever area you are strengthening. But as you can see that because it's an already cured material, you don't have too much flexibility to work with it, because you cannot bend it on site. You cannot go according to the shape of structure if there is awkward shape and all. For that reason, fabric system is quite commonly used around the world. The plate has its own uses. For example, whenever you're strengthening a metallic structure like steel, wrought iron, cast iron, you will use plate because you need to match the modulus of the parent material. Also, plate gives you a much smoother profile as compared to the fabric. But in most of the concrete strengthening schemes, you end up using fabric system because you may have to do column strengthening going around the column or around the beam for shear strengthening, and that you can do using this system. The same theory works with glass fiber as well. So there is also GFRP material, which is glass fiber reinforced polymers. The similar sort of theory works here as well. So in the fibers, you have glass fiber here and the same epoxy. So whenever I say GFRP, people usually get confused between GFRP and GRP. So the difference between those two materials is that this material GFRP is a structural material because it has a continuous strand of glass fiber which can transfer the stresses, as compared to chopped strands of glass fiber in an epoxy matrix, which is used to make formwork or liner. So that's not a structural material, whereas this is. Now, these are the fire protection systems available in the industry. So there are different types of fire protection system which has been tested with carbon fiber and approved by UL. So some of the common systems are like an intumescent paint coating, which provides up to 2 hours fire rating. Then there is a cementitious fire protection system, which can provide up to 4 hours fire rating, and these specially manufactured fire boards. So if needed, FRP can be fire protected as well, but in most situation, your FRP doesn't need special fire protection system because structurally, your structure would be strong enough to carry the fire limit state load. And you don't need FRP contribution there. So in those instances, you don't need fire protection, but in wherever you need it, these are the systems which can be used. Right, this is a typical stress strain behavior of FRP in comparison with mild steel. So there are very important things you'll note on this stress strain behavior, which is quite important for you as designers or structural engineers. So we all can see this black curve, which is the behavior of steel. We design it on the yield stress, and it's quite straightforward that way. The top green line is behavior of carbon fiber. Bottom green line is behavior of glass fiber. From this curve, you could see that carbon is stronger than steel, and glass has better deformability or ductility, if you like. So based on this curve and the requirement, it is decided that which material to be used for a particular project and at what strain level it should be designed. Now, in terms of, for example, product selection, if you are strengthening a structure like in London, then most of the cases you do probably you will not design them for any earthquake forces or anything. So you'll end up using carbon fiber because you're looking for pure strength out of it rather than, any more ductility. But if you're strengthening a structure in America or some part of the Europe where earthquake is a dominant design criteria, in that instance, you end up using glass fiber because you want to get more ductility in the structure. And glass fiber will provide you more elasticity. So that's why you use glass fiber in seismic retrofits and all that. The other thing you'll note on this curve is that both carbon fiber or glass fiber or any other FRP for that matter has a linear elastic behavior until their failure. So there's no yield point in any of the carbon fiber or glass fiber. So it doesn't give you warning before failure. The ultimate failure in FRP is brittle in nature. And for that reason, FRP design will always be a strain limit design. So there's nothing to do with the tensile stresses given on the datasheet. So generally what people do is that they approach the FRP design similar to they approach the steel design. So in steel design, the yield stress of the steel, the force you need to carry, divide that force with the stress, that will give you the area of steel required. But in FRP design, it's slightly different. So how you design FRP is basically you take the modulus of material from the datasheet and the thickness of material. Those are the only two things you use from the datasheet. Then you limit the strain depending on the guideline you're following. So if you're using ACI for a particular instance, it might be a little lenient, whereas TR55 could be conservative or vice versa. So that will give you a strain value for that particular type of strengthening for that particular scenario. You multiply that strain with the modulus from the datasheet. That will give you the design stress for that element strengthening, and you will use that stress to calculate the area of FRP. So I'll say it again that FRP design will always be a strain limit design, and you have to derive the tensile stress of the FRP depending on the project you're working on and type of element you're strengthening. Now this curve here explains the very first thing which I said, that this is a composite material. So you have at least two materials mixed together to make FRP. So it could be a fiber that is mixed with epoxy matrix. That fiber could be carbon fiber, glass fiber, aramid, basalt. There are many types of fibers available. When you mix it with epoxy matrix, the actual property of the final cured laminate drops slightly. So in the design, we should always consider this final cured laminate property. So that's the correct way to design FRP. There are still people out there who do design based on dry fiber property, which is okay. You could do that, but there are many other safety factors you should use in there. But ultimately, if you're using a fabric system, it is the best practice to design it based on the final cured laminate property. Now, this is a part of service we provide here in the UK and Europe. You guys can use it as well if you want. So in this case, basically what we are saying is that we understand that if you have not designed carbon fiber or FRP in past, you may be reluctant in doing so now because you're quite comfortable in working with steel and concrete. So what we say that if you come across any project or any situation where you just want to explore whether FRP strengthening will work or not, then send us this information, which is basically what element you're looking to strengthen. what is section properties in terms of the size, reinforcement, grade of steel, grade of concrete, and all those things, and then provide us the loads, like what moment it can carry right now, what moment you want it to carry in proposed state, and all those things. Once we get that information, we'll do an initial analysis, which we call feasibility study, and let you know whether it is feasible to strengthen that element or not with carbon fiber. And if it is feasible, then how much FRP will be needed and how long will it take to do that work. Everything will be put into a report, which you can take to your client, show them this alternative way to strengthen. If everybody's happy with the cost given in the report, then they will come into effect. Otherwise, until that point of time, we don't charge anything. So it's a no obligation design support, and I seriously recommend to use this service because it gives you your own experience of working with FRP, and you can understand it yourself, that what are the limitations and where it can work, where it can't work, and all. And all it is going to cost you is probably just a phone call or an email. So I'd again seriously recommend to use this service. Right, we'll see what can be strengthened with carbon fiber. So we'll see different types of elements, types of strengthening, project examples and all. So the most common element you come across, which is strengthened with FRP or carbon fiber generally, is flexural element, which could be beams and slabs. Now, generally, flexural elements are strengthened for sagging and hogging moments. So you apply FRP at the underside for sagging moments, on top for hogging moments. Up to an extent, you can also strengthen slabs for punching shear. As you could see here, this is done in Manchester project, where we strengthened all the column heads with carbon fiber to increase its punching shear resistance. Now, if we try to understand this in very simple schematic, that what's the theory behind it, then you could see it here. So FRP has very good properties in tension. So it gives you the tensile strength you want in your structure. And for that reason, FRP is always applied onto the tensile face of the element. FRP is not recommended to improve the compressive resistance of the structure, purely because FRP doesn't even have a significant cross section. Because if you remember, I said FRP has typical thickness of 1 millimeter per layer. So even if you put multiple layer, you're not increasing section modulus significantly. So for that reason, it is only used to improve the tensile resistance. So based on that theory, you apply it at the mid span, at the underside to improve the sagging moment resistance, on top near the supports to improve the hogging moment resistance. In this as well, there is a common detailing mistake people make. So what they do is they take the FRP up to the ends and support and stop it there. Now, as structural engineers, we know that if we are strengthening this for hogging moments, that's the location where we have the peak moment or peak stresses. If you curtail the reinforcement at the peak stress area, then there's no point in doing that strengthening, because you want some sort of development length or anchorage length beyond that point. That is the same principle works in the traditional reinforcement as well. So in this case as well, there has to be some sort of anchorage detail provided in this situation. So you can drill through the column, use the carbon fiber anchors going into the ends, or you can go up the column around it. So there has to be some sort of anchorage detail here. Now, in terms of shear strengthening for the beams, if you can imagine putting like a link or a stirrup from the outside of a beam, that's how we do shear strengthening. So that's why this application is also called U-wrap strengthening. And then again, we can use the same anchors drilled into the slab or into the beam, and they provide similar effect as in closed loop. And this we found when we did a research in University of Ghent, Belgium, that if you're able to drill these anchors diagonally, they provide similar effect as in closed loop. Now, just to show you some bigger anchors, so there are two types of anchors you get. One are blind anchors or normal anchors, in which case how it works is that you drill a hole into the concrete, you saturate the anchor, put half of that anchor into the drilled hole, split the remaining half on face, put one more layer on top of it. So this will become one unit which will cure simultaneously, but it is actually going into concrete. So it provides you additional anchorage and bond capacity, so your debonding and delamination failure will not happen. Then there are these bigger and super anchors, which we call them. So they are specially designed anchors. They are used or designed for a particular force. As in case of this example, where we were strengthening the slab for hogging moments, we are basically looking downwards onto the column or slab area. There was a column in the way, as I explained on the previous slide. So in this instance, we drilled hole through the column, used these bigger anchors, pass them through that drilled hole, split them on both sides like a dovetail, put one more layer on top of it. So now after curing, these anchors become as a tie, which is transferring force from one side to another side. Or in other words, you've got a continuous top reinforcement in that location. So that's how you should do the hogging moment strengthening using carbon fiber with a proper anchorage detail. Now the same thing, if you can assume tilted 90 degree, it becomes like a shear core scenario. So this is a vertical wall. This is slab junction. In this instance, we strengthen this 11-story shear core, and at every slab level, we use these anchors, drill through the slab to transfer the strengthening from floor above to floor below. And ultimately, everything was anchored into the pile cap. So that's how you had the continuous reinforcement vertically onto the wall, which is going or transferring back to the foundation. Right, here is a project example from UK. So this is a London project where we did the slab strengthening. So in this instance, this is also an example of the construction error. So what happened here was that this is a new build reinforced concrete frame, as you could see here, with concrete column and flat slabs. There are 3 tower blocks, A, B, and C at the back. So after the construction of this frame, the contractor who was working there has gone into administration, or ultimately got bankrupt, in other words. So before passing his work to the new contractor, the client has ordered some investigative works. So when they scanned these slabs or did the Faro scan on these slabs, they found that there is reinforcement missing in the flat slab. So there was not one area, there were around 400 plus areas where the previous contractor did not put the required reinforcement as per the design. So structure got condemned, client was asked to demolish and rebuild. Now you can imagine, if you demolish this kind of structure, it will be first of all a lot of money, and also the amount of money you have spent so far to get up to this level will be of no use. So we worked with new consulting engineer, designed each and every area individually for that additional reinforcement, and provided in form of carbon fiber. Now this strengthening was mainly around the column area, as in case of that standard, additional mesh reinforcement we provide. The same thing was done using carbon fiber. So this was basically for hogging moment and punching shear. And ultimately, this is the fire protection system applied on top of it. So we saved a lot of money for client by not demolishing and rebuilding. And this was the quickest way for them to strengthen structure and start building it, again and move forward. Here is a brief video which shows you the application part. So the first thing you do is surface preparation, which is done by grinding the area. Then you clean the area, it needs to be dust free, followed on by priming. Priming is always done using pure epoxy so it can soak into concrete. Then they apply first coat of thickened epoxy, which is the white color epoxy you're seeing, and they unroll the first layer of carbon fiber. Then provide another coat of epoxy, another layer of carbon fiber, and that's how they build up the number of layers. Now, because this is an application on top of the slab, you're not restricted in how many layers you can apply in one shift or one day. But if it was more than, like if it was vertical application or over the, underside of a slab, then you can only apply 3 layers in one day. After that, you have to wait for it to initially set and cure, and then you can apply further layers. And the initial setting time is 4 to 6 hours. And it will be 100% cured in 72 hours in ambient condition. So you can reload your structure back to its new capacity in 3 days. So that's how they do application. But this is also, you'll note here that the carbon fiber which this guy is applying is actually in wet condition. So it was saturated in a different area on same site. So when he's applying, it's in the wet condition, and that's why it is called wet layup method. And that is the correct way to do the FRP application. There are still people out there who do dry layup. So in dry layup, what you do, you just prime the area using pure epoxy and then try and patch a dry fiber with your hands on it and put another coat of epoxy on that dry fiber. Now that dryness in the fiber would lead to a debonding and delamination failure because you cannot guarantee the 100% resin impregnation. And for that reason, the dry layup is more or less abandoned in the UK, and it should not be used in the UK and Europe, and it should not be used anywhere. So if you ever come across, especially the fabric application in your country on one of your project, make sure contractor is doing wet layup method. This video shows you that saturation part. So this is a hand saturation example because these are the small lengths which they are applying. That's why they are doing it by hand. If they were longer lengths, they'll use a machine called saturator machine. Now, because they are doing it by hand, there is an additional quality control check he needs to do, which you'll just see right now. So after saturating this piece on both sides, he will wait, as you could see here. So by this way, what you're seeing is that the dry weight of fiber. After saturating, he has taken the saturated weight. So it tells you the amount of epoxy he has used in saturating that piece prior to applying it in the actual area. So by that way, you can make sure that application is actually done as wet layup method and not dry layup. And with us at CCUK, we do not subcontract the application purely for, the quality control process only, because in FRP strengthening, the most important part is the application. The design and everything can be done, but the most important thing is application. And if it is not done correctly, it will not do what it is intended to do. And for that reason, we do not subcontract the application part. This is another project from London. It's London South Bank University, which is on Elephant and Castle. And this is one of the biggest university in London. So in this case as well, we did this strengthening for flexural elements only, mainly for waffle slab and the beam strengthening. And this reason for the strengthening was that they were remodeling the university. They were changing the position of library from one area to another area, introducing new stair core and everything. And for that reason, these traditional 1960s waffle floor slab needed strengthening. Now, structurally, for some bizarre reason, there is no reinforcement in these transverse ribs. So it was treated as one-way spanning rib slab. So for that reason, we treated it as T-beams or row of T-beams. We applied FRP plate at the underside for flexural strengthening. This is the shear strengthening of individual waffle with the anchors. This is the top strengthening of these same ribs for hogging moments. So that's why the amount of carbon fiber used on that project was around 8,000 meters square, which is the biggest quantity of carbon fiber in a building environment in the UK. We used around 12,000 shear anchors to do the shear strengthening, also around 1,000 square meter of fire protection system to get the fire protection of the area after the strengthening. So that's how the project was done. The reason why I'm showing this project on this presentation is that if you go on the iStructE website and the Sustainability Award for 2021, the project engineer for this project, Eckersley O'Callaghan, won the award for this particular project from iStructE. The reason for that was that the overall CO2 emission on this project was just 49 kg CO2 emission per meter square, which is less than half of this 105 kg CO2, which is 2030 LETI target. And in this 49 as well, only the 3% was contributed by carbon fiber. The rest was still traditional steel and concrete and all. So you could see the advantage of using FRP from sustainable construction point of view as well. It saves you a lot of CO2 emissions and all those things, purely because you are retaining a lot of structure, reducing the use of traditional steel and concrete, and that gives you a huge advantage. So you could read this paper on iStructE. I think this paper is still available on iStructE website. This is another type of strengthening which is quite commonly done here in the UK using carbon fiber, which is strengthening for new openings or penetrations through reinforced concrete elements. So there are some, small service riser penetrations, big riser openings. This is a door opening through a shear core, and everything, can be done with carbon fiber. And the traditional approach for this is the traditional trimmer steel beams. So usually what people do, they design some trimmer steel, transfer it to surrounding beams, and that's how they deal with the situation. Same thing can be done with carbon fiber as well. The first and most important check you should run is that by creating these openings, if you are compromising the global stiffness or overall stability of the structure or not. If your answer is no, the stability is not compromised, then you can use carbon fiber. There is a good chance that you can find a solution with carbon fiber. But if you're compromising the stability, then obviously traditional steel is a better option. Now, in terms of design, there are two ways you can approach it. One is force equivalency, which is a very straightforward design approach. So in that case, if you have the smaller openings like this, you can design it based on the force generated by loss of rebar. So when you cut these openings, you'll cut some reinforcement in the slab, and those rebars will generate some additional tensile force, and you can design these FRP strips on all four sides to carry those force. So that's a very straightforward approach in that way. But if you have bigger openings like this here and this riser openings, usually we suggest to model the slab or the concrete element and see the before and after stresses and design FRP for actual stresses afterwards. Here's a project example for that. This is from Birmingham in the UK. So there they needed new penetrations through the beam for the M&E and electrical works and pipes and all those things. Now, in this case as well, we use the force equivalency approach. When they were coring these cores, they were going to cut some links in the beam. So we designed these FRP strips to carry the force equivalent to those links. Once the FRP was cured, then they core the opening. So as soon as you cut the rebar, the force will transfer to the FRP and there will be no localized concentration. From architect's point of view, this was the quite neat solution because they're not putting additional steel underneath. They can plaster over it and it will be all concealed and everything. So that's the reason that architect also loved the solution as well. Column strengthening. This is one of the easiest strengthening to do with the FRP. The reason for that is that here we are working on confinement theory. So what we are basically doing is that we are confining the concrete with a much stronger material from the outside. So when the load comes on top of it, the column could dilate. FRP provide resistance to that dilation, and that's how it's strengthened. And for that reason, circular is the best shape to strengthen because you have stresses even throughout the perimeter. But if you have the columns which are square and rectangular, you can still work on confinement theory. But there are two things you need to make sure. First, you need to round off these corners to a minimum radius of 20 millimeter. That's a design requirement from TR 55. And in addition to that, the aspect ratio of the column should be up to 2. Because if you have more than 2 aspect ratio, then technically you should do combined bending and axial analysis and see if there are any additional moments for which you need to apply longitudinal FRP or just the confinement could work there. So that's the approach for the design of the column. Here's a project example for that, another London project. So in this case as well, the same theme here. They had an existing building. They added one more story on top of it. The columns in the basement got overstressed and needed strengthening. But these are not reinforced concrete columns. They are steel columns encased in concrete. Now the solution engineer proposed there was to take this encasement off, weld another plate of the steel onto the flanges of the column and recast this encasement. And for that reason, they needed around 80 of the columns needed strengthening. So if you go with the same method, it will be a very destructive way to strengthen. So when we looked into this project along with the engineer, we found that there is some longitudinal rebar and links available in this encasement. Now, according to Eurocode, there is a clause in Eurocode that if you have the minimum longitudinal rebar and links present in an encasement, then you can account for that encasement as contributing an axial load bearing capacity, as in case of a composite column. So when that was done, column needed strengthening gone down from 80 to 20, and the 20 columns needed strengthening purely because strength of this concrete encasement was just less than 20 MPa, which is the minimum requirement. So that was our design goal. We had to confine the column such a way that the strength becomes 20 MPa and more. So only 2 layers of carbon fiber needed. So again, the solution was to take the encasement off and everything from there. Just leave the encasement and then just wrap it with 2 layers of carbon fiber, which was the quickest way to strengthen them. Here's a brief video for that. So again, the same as you've seen in the slab strengthening, the first thing is surface preparation, followed on by cleaning. The only additional preparation part you could have in this is probably rounding off of these corners if they are not already rounded off or chamfered. That's the only additional preparation you may have to do in the column. But after that, you follow the same process. You prime it using pure epoxy, apply the first coat of thickened epoxy, then apply the first layer of carbon fiber, the next coat of epoxy, next layer, and that's how you build up the number of layers. Now, because it's a vertical element, you can only apply 3 layers in one day or one shift. After that, you have to come back next day to apply further layers. But because this was just a 2-layer application, everything was done in once only. Now, in this particular time-lapse video, you could easily see the benefit of using fabric systems on a concrete structure, because it is just a fiber, you could easily go wrap around the column and provide a jacket around it. But if you use plate, obviously you can't do this kind of strengthening with the plates. Everything you're seeing in this video from start to finish, this final layer application, from preparation to this application, everything took us just 6 hours. So in 6 hours, this column was strengthened. So you could see how quick this strengthening is. And now if you compare it with any other traditional method of putting additional steel beams, a steel section, or taking the encasement off, welding the steel and all those things, that will take much longer than 6 hours on a particular column. This is another example of column strengthening. This is another new build structure from London. It's near Nine Elms in London, Vauxhall. There are 2 tower blocks you could see here, one in the front, one in the back. So it's a new build structure still under construction, but in this case, the strengthening requirement was not because of a design error or construction error. It is very well designed, very well constructed project. The issue there was the client changing their mind at the very last moment. So what happened was that there was supposed to be a link bridge between these 2 tower blocks. That link bridge was going to be a precast concrete bridge, which had no connection with these 2 buildings. But in the end, client changed his mind and he wanted a steel bridge instead. Now that steel bridge needed a connection with this plate, with this column. It needed to be a plate to be connected here on which the bridge can be connected. This column is not designed for that load and needed strengthening. So they asked their on-site contractor to cast another concrete jacket around it. They said it can be done. It will take 2 weeks to do the work, and after that 28 days for it to cure. They did not have that much time because bridge was already in transit and there is no way they could store it on site. So we did the strengthening using carbon fiber when it was feasible. They gave us the order. We started work on Friday evening, finished it by Monday morning, and the following weekend they were able to connect the first plate. So it was the quickest way, and purely because of the time constraints, they used carbon fiber and it was the best solution. From architect's point of view, they loved this solution better than the concrete jacketing because obviously the column size hasn't changed significantly, so they could continue with the same facade. Right, obviously there are some climatic restriction when you do FRP application. So in terms of the temperature readings and everything, you need minimum 4 degrees centigrade for application of FRP. Your humidity should be less than 85%. So all those things is not easy to get all around the year, especially here in the UK. In winter months, we don't get those kind of temperature. So we create that kind of artificial environment by putting the heating in the area and creating those enclosures and doing that. But yeah, if that's needed, that can be done as well. Otherwise, as I said, you need minimum 4 degrees centigrade for the application of FRP. Then in terms of the testing, how do you test that FRP has been applied correctly? So usually FRP is tested for two types of failure. So one is debonding and delamination, which is usually on bond critical application. And the other one is material properties. So for debonding and delamination, all you do is just a pull-off test onto the strengthened element, especially in the concrete. So what we do is that whenever we strengthening element, we put a sacrificial patch on the same element. So this beam was strengthened for flexure, we put a patch on the side of it, and after that we performed a pull-off test after 100% curing. Now the difference between this pull-off test and the concrete pull-off test is that in concrete pull-off test, we look out for a strength in terms of number, like whether it's 3 MPa, 4 MPa, depending on grade of concrete. But in FRP, we are not interested in that number. We are more interested in mode of failure. So what we want to see is that when you do this pull-off test, it should not come out from substrate only, or it should not come out from another layer of FRP if there are multiple layers. So in this instance, you could see when we did this pull-off test, it took out some concrete with it. So which shows your bond strength between FRP and concrete is much higher than your actual concrete failure strength. So ultimately, if anything goes wrong onto this structure, that will be the concrete crushing and not the bond between FRP and concrete. And that's the pass criteria for a pull-off test on any bond critical application. And then the second example or test you do, especially when you're using a fabric system, you should do a composite laminate testing. So you cast these 12-inch by 12-inch plates, let them cure on site, send it to independent laboratory. They'll cast a coupon out of them like this and do a tensile test. Those tensile properties should match with the data sheet of material or should match with the design values which you've used in your design. And that's the pass criteria for this test. And you can relate this to like concrete cube casting, which we do on structures. And finally, this question we get asked a lot: can we drill through carbon fiber? Can we fix through this and all? So usually the answer is no. It's a structural material. You should avoid as much as possible fixing through the carbon fiber. And for that reason, we leave these kind of gaps for the M&E guys to come and use them for false sealing or these services and all those things. But in instances where they drill through carbon fiber, either knowingly or unknowingly, we may have to go back and repair it. So like in this instance, they cored through carbon fiber. So we went back on site, apply additional layer on the side of it to account for the loss of area in this particular section. So what we usually say that if you have to drill through carbon fiber or fix through carbon fiber, you should let the designer know in advance so that they can have some design allowance for it. And when you do those fixings, you don't have to go back and repair it. The repair is very simple. As I said, you just go apply additional layers, but why repair it when we can design for it? I think that's about it. I've pretty much covered everything, so I'll pass it back on to Steve.
Thanks, Jay. Thanks, everybody. Quite a lot for you guys to take on. We are obviously have tried to cover all the very aspects of projects that we do here in the UK. But just some summary points, just to finally, hopefully nail who we are. We are the #1 company in the UK for using carbon fibre design and application. Complete durable and economic solution. It can save time and money. We've showboated. We've shown you some really great big projects. We do small projects also, but we've seen a really big uptake in the UK over the last 10 years with main contractors. Main contractors are now going to the designers, to you guys, to say, can you give us a carbon fiber solution? Because it can be quicker. It can be expensive, but it's quicker. So when you're looking to reduce your program times on site, it's something which is really important to them. The systems, procedures, and the testing. This is as what Jayesh has said. If Jay gives my teams or our guys on site a design and it's not applied correctly, then you're going to have a problem. It's absolutely critical that the application process is followed, and this is why none of anything that we do is subcontracted out. It's all kept in-house. Our guys are with us for a minimum of 2 years before they're allowed to apply carbon fiber. And this is hopefully in the UK anyway, is going to be the norm on what we do. And finally, when, where, and why? Not as much for you guys in South Africa, but in the UK, we're saying to our clients, what is it? It's going to cost you a phone call or an email. We'll look at what information you've got and we'll turn that into an outline design with some timescales. You go back to your client, you say, listen, we're going to look to use carbon fiber, and we'll take it from there. So that's our presentation. We hope that, as we said earlier on, it's about ideas. We don't know what you guys are working on or what you may be working on, but hopefully it's give you some sort of an idea on what you can be or how you can use carbon fiber on your project.